Section 7.5, we are looking at systems of inequalities. We have been solving systems of equalities, both linear ones and looking at ones that weren't necessarily linear. We are shifting now, though, to systems of inequalities. So we're going to start out just how do we graph a linear inequality? All right, review that. How do we graph a system of linear inequalities? And how do we use that graph to solve the system? Okay. Like I said, we're going to start a little bit of the linear programming today, and then we'll wrap up the harder ones on Monday. Okay? All right. So an ordered pair is a solution of an inequality if we can substitute it into our equation or our inequalities and it works. All right? It makes a true statement. So the point AB is a solution to the inequality if we can substitute that ordered pair in for x and y, and it satisfies the inequality. So in this example, is the ordered pair 2, 5 a solution to this inequality? Well, let's plug it in. If we put 5 in for y, and we put a 2 in for x, does it give us a true statement? We end up with 5 being less than 7, which is true, right? If you have a true statement, then it is a solution. Okay? If you get a false statement, then it's not a solution. A graph of an inequality represents all the solutions of the inequality, and we call it a half plane. So like half of our coordinate plane. Now, you have done everything we're doing today, you've done in Algebra 2. So today is just review. It says, remember that boundary lines are an important part of your graphical representation. So the shaded part here is that half plane that we were talking about. The black or the dotted blue line here in this case is considered the boundary line. Okay? And it's an important distinction as to whether it's solid or dotted. Okay? If it is dotted, it means we're getting very close to that line, but we aren't actually on the line. So any points on the line would not be considered solutions to your system or to your inequality. Okay? If it's a solid line, then those points are included. So to graph an inequality, pretend there's just an equal sign in there. All right? Graph the boundary with the equal sign, and then decide if there's no equal sign, if it was strictly less than or greater than, then make it dotted. If it was less than or equal to or greater than or equal to, then you make it a solid boundary. The last step is to take a point and check it. Do you remember from last year what was the easy point that we checked? 0, 0. When was the only time we couldn't test the origin? Yeah, if your boundary line or curve or whatever it was actually went through the origin, right? So you're testing a point that's not on the boundary. In other words, if this was my picture, all right, I had this dotted line here, I'm going to pick a point. We said check the origin, okay? If we had put the origin into this inequality, put 0, 0 in, it made a true statement, which is why they shaded this side of it. If it had given us a false statement, we would shade the opposite side. Okay? All right, so let's try one. It says, draw the graph of y is greater than or equal to 2x plus 3. State the boundary of the region. So they've given us a nice linear inequality. It is solved for y, so we have it basically in that y equals mx plus b form. Okay? So the boundary is the actual line with the equal sign instead of the inequality symbol. Okay? So we're going to start by graphing that boundary line. This says I have a y-intercept of 3, and I have a slope of 2. So we're going to go from there up 2 over 1. Or remember, you can go down 2 and back 1. Reverse the 2. Okay? And then we're going to draw a line through it. Now, we have to decide, is it solid or dotted? Okay? Because it says it can actually equal the 2x plus 3, we're going to make this a solid line. And then we test our point. Can we test the origin? Okay. So we're going to test the point 0, 0. We're going to plug it into y is greater than or equal to 2x plus 3, which means we get 0 is greater than or equal to 2 times 0 plus 3. Is that a true statement? Is 0 greater than or equal to 3? Okay, so if you get a false statement like this, and we don't want the origin, right, we're going to shade the opposite side. So we're going to shade up here. So the half plane that I would want is that top part. Okay. Couple things to check on your graph. Did you put arrows at the end of your line? Okay, some picky little details, but that line does extend. All right. Is the boundary included? So any points on my line are actually solutions to the inequality as well as all the points that I shaded in the upper left part. Okay, so it is included in my solutions. Okay. All right, the next two. Notice that they are inequalities, but there's only one variable. So take a second, talk at your tables. X equaling 2 and y equaling -3. What would the boundary line look like? So what would the boundary line look like for x is greater than or equal to 2? We ignore the inequality, right? We just look at, well, x has to equal 2. What kind of line is that? A vertical line, right? We want all the points on our coordinate plane where x is 2. That would be everything in a vertical line here. And is it solid or dotted? Solid. All right, so we have a solid line here at 2. And then where would all the values for x that are greater than 2 be? All the things to the right. We can test a point just like we did for the oblique or slanted lines, but it's usually pretty obvious for your vertical and horizontal where you have values that work. But we could test a point. We could put 0 in there. Is 0 greater than or equal to 2? Then we don't want the origin. We would want this side. Okay. Is the boundary included? Okay. And then the second one, y is less than -3. Our boundary, remember, is just y equals -3. And what does that look like? I see some horizontal lines being shown to me. Yes, we have a horizontal line at -3. Is it included? So if it's not included, we want to make it a dotted line. So we have a dotted horizontal line at -3. And then, again, we can test the origin. Is 0 less than -3? Is 0 less than -3? No, so we don't want the origin. We want the points down here. Okay? So the part we shaded fits all the y values that are smaller than -3. Questions on either of those? All right. Everything we've done so far has been linear. What's this next one going to look like? Good. It's a parabola. Can you describe where it would be located? 3 down from the origin. Perfect. So we are looking for a parabola that has been shifted 3 down. Our boundary, remember we just take out the inequality symbol, y equals x squared minus 3. Is the boundary included? Okay. So we're going to have a solid boundary for our parabola. We said it's shifted down 3 from the origin. So we're going to have the vertex here at -3. And then how do we find other points on our parabola? You have a couple options. You could plot just y equals x squared. You should know where those points are and shift everything down 3. You can make a t-chart, right? We've graphed this before. We know we have 0, -3. What do we get if we put a 1 and a 2 in? If we plug 1 in here, 1 squared minus 3 is negative 2. If we put a 2 in there, 2 squared minus 3. Okay, so let's plot 1, negative 2, and 2, 1. And then how do we get the other side of our parabola? Yeah, just use the symmetry. Flip them over. So we have a point here and here. Okay, and we said it's a solid curve. We are including the boundary. Can we test the origin? Yes, our parabola doesn't go through the origin, so we can use that as our test point. So we have 0 is greater than or equal to 0 squared minus 3. Is 0 greater than or equal to negative 3? So we want the part that has the origin in it, which is everything inside our parabola, right? The origin is inside, so we're going to shade all of this. Questions on that one? All right. We are shifting now to a system of inequalities. Instead of just a single inequality, we are going to be graphing several of them on the same grid. Okay? It says a solution of a system of inequalities in x and y is an ordered pair xy that satisfies each inequality in the system. It has to work for all of them. What kinds of shapes are we going to have in this one? Top one is a parabola, yes? Our parent function for a parabola, just our basic one. And the second one is linear. Okay, so we have a parabola and a line. Are the boundaries included? Either one? No. Neither one has an equal sign, so the boundaries are not included. So any points on those boundaries are not solutions. Okay? All right. So let's graph the first one. Y is greater than x squared. We're going to graph y equals x squared. We have a vertex at the origin. What other points are on my parent function parabola? 1, 1, and 2, 4, 3, 9. Okay, flip them over to get to your other side. And we said this has to be dotted. So draw a dotted parabola through those points. And let's test a point. Can we test the origin? No, this time the origin is on that boundary. So let's pick another point. I'm going to pick the point 0, 2. Okay? You can pick any point you want as long as it's not on your parabola. I'm just going to pick an easy one, 0, 2. If we plug that in, we have 2 is greater than 0 squared. Is that true? Yes, 2 is greater than 0. So any points inside the parabola are going to be solutions? Yes? Okay, shade it very lightly. I'm not going to draw it up here because there's no way to make it really light, but shade lightly the space inside your parabola. Okay, the second one we said was a line. It is not in slope-intercept form, so we have two options. We can rearrange it and get it into slope-intercept form, or we can find the x and y intercepts and graph it that way. Okay, I'm going to leave it up to you which one you want to do. I'm going to find the intercepts up here, but if you would rather rearrange it and get it solved for y, you certainly can. All right, if we plug a 0 in for y, remember we're pretending there's an equal sign here, so 2x equals 4, x would have to be 2. If we put a 0 in for x, we're saying 3y has to equal 4, so what do we get? We get 4/3. Okay, not quite as nice, right? It's not going to be right on a grid mark, but we can make do. So let's plot those points. 2, 0, and 0, 1 1/3. And we said this is also a dotted line. Yes? Okay, can we test the origin for that dotted line? All right, let's try it. If we put 0 in, we've got 2 times 0 plus 3 times 0 is less than 4. 0 is less than 4? So we're shading the part where the origin is. We're shading below the green line. Okay, so on your graph, you should have lightly shaded the space inside the parabola and the space below my green line. Yes? Where do they overlap? The part where they overlap is your solution. It's the part that have solutions that work in both inequalities. All right, so my final answer would be this space right in here. Okay, now be careful because the boundary lines are not included. Okay. All right, how many have graphed inequalities on their calculators? There's an app in your calculator called Inequals. If your calculators were cleared for the ACT recently, that might be gone. So just go into your apps and scroll down and see if you have one that says Inequals. Okay. If you have it, you can turn it on. Keep in mind, though, that you are going to be expected to know how to graph these inequalities by hand. So your calculator would just be a check for you. Okay. What that program does is it creates the inequality symbols at the bottom of your y equals screen. So instead of a y equals, you can change it to that. Okay? All right, we are going to graph the rest of this by hand today. If you have questions about your calculators, you certainly can come up and ask me. Okay? Examples 5 and 6. If you look at the system of inequalities, it's the same system for both. So we are graphing it in one, and we're actually solving it again in the next one. All right, we're taking it a step further. So you have a choice. If you would like to do the whole thing where we have example 6 written, you certainly can. You'll want to write a little bit smaller just so you have room for everything in that one, but they are really tied together. Okay? So we are solving a system of 4 inequalities. What do the bottom 2 inequalities imply? X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. We're in what? We're in quadrant 1, right? That's the only part on my coordinate plane where X and Y are both greater than or equal to 0. Okay? So if you look at a system that has a lot of inequalities, check to see if there are some that are more obvious. Okay? These two combined just mean we are in quadrant 1. So I'm not going to graph and shade that. I'm just going to know, okay, I'm stuck with quadrant 1, and then I'll look at the other two and restrict it to quadrant 1. Okay? The other 2 inequalities represent lines. So what we're looking at here is having 2 lines, and we're trying to find where their shading part overlaps. Okay? First one, 2x plus y is less than or equal to 10. Our boundary, would it be included? Yes? Okay. Could we rearrange this into slope-intercept form pretty easily? Yeah. We're going to look at y equals negative 2x plus 10 as our boundary for this one. So we are going to start at 10 and do a negative 2 slope. For my graph here, I am going to just assume this is quadrant 1. So my axes are on the ends here. Okay? All right. So we're starting up at 10. And we're doing a -2 slope. All right, agree, disagree? Okay. Go ahead and draw a line. Try to make it as straight as possible. So if you want to use the edge of a notebook or something. Okay. Which part would we be shading? Are we shading towards that origin? Well, let's test a point. If we put 0, 0 in here, does it work? Okay, so we are shading this direction towards the origin. Again, shade it lightly on your paper. I'm going to wait and shade my final answer since I can't make it light. Okay, let's look at the second one. We have 2x plus 3y is less than or equal to 14. It's not in slope-intercept form. I could get it in slope-intercept form, but either way I'm going to have some fractions to deal with. So for this one, I'm going to go ahead and find my x and y intercepts, since one of them will come out nicely. If I put a 0 in for y, what do I get for x? Okay. If I put a 0 in for x, what do I get for y? I get 14/3, which would be 4 2/3. Okay, so we are going to have one point that's not quite as exact for us. All right, let's plot those. We want 7, 0, and then we want 4 2/3 on the y-axis. Okay, again, we need a straight line through those. Okay. Does the origin work for that one as well? If we put 0, 0 in here, the whole left side becomes 0. Is that less than or equal to 14? Okay. So we are shading below the red and below the blue. So the part where your two shadings have overlapped should be this section right in here. We okay with that? So if it just says to solve the system, we've done that. Any point in this green area is a solution. How about the boundaries? Are they included? Okay, so basically we are saying that anything along here, use a different color here, along here, come on, this direction and this direction, right? All of this would be considered a solution to that system. Yes? Okay. Before we go on to example 6, we're going to be bouncing back and finding some things from this picture. So I'm going to have you, in example 6, write down what are the corner points of this region. Okay? So what is this point here? 0, 0. So by example 6, write 0, 0. Okay? What is this point here? 5, 0. Okay, jot that one down. How about this point on the y-axis? 0, 4 2/3. Okay. And then what about where the two lines intersect? This point here. It looks like 4, 2. Would you agree with that? How could we check to see if that is truly the right point? Plug it in. It has to work on my two oblique lines, right? The two slanted ones. So if I plug it in, does it work? 2 times 4 is 8 plus 2 is 10. All right, and you want it to be actually equal to 10, right? It's on the boundary. And then putting it here, we have a 4 here, a 2 here. We get 8 plus 6. Does that equal 14? Okay. if you are not careful with your graphs, it's going to be hard to figure out what that point is just by looking at it. Okay, so that's why I'm saying take some time. Don't make your graphs so tiny that you can't tell what it is. All right, spread them out as the best you can. In other words, if you have space, use it. Don't make one tick mark be 100 units when you can make it be 10, right? You want to spread it out enough so you can tell where those points cross. If you can't tell, you can always go back to using algebra and just solve those two equations together, all right, using linear combination, elimination, substitution, whatever, and find where they actually intersect, okay? All right, so you have those 4 corner points written down? Perfect. All right, so the idea behind linear programming, what we just did in example 5 is the start of it. It's just not all of it. It says sometimes decision making in management science requires that we find a minimum or a maximum of a linear function called an objective function over a set of points. Okay? Sometimes they want us to find a minimum or a maximum. So that objective function might be a function that represents our profits, all right? And we want to maximize our profits. Or it might be a function that shows us what our costs are and we want to minimize our costs. Does that make sense? Okay. Such a problem is a linear programming problem. We are given information that places limits on our resources. This information provides what we call constraints. So all of these inequalities that we graphed in example 5, those are the constraints, right? Those are the things that are limiting what I'm allowed to use. Okay? The solution of the system provides us with a feasible region. So that part that we darkened in black on the previous screen, that's called the feasible region. And it says if our linear programming problem has a solution, it will occur at one of the vertices of that feasible region, one of those corner points. That's why I had you write down where the corners were, because the solution to this system, to the linear programming part of it, is going to be one of those points. Okay? So very quickly, you should have a picture like this from example 5, yes? And we said our vertices were we had 0, 0. We had, what else? 5, 0. 2 more. 0, 4 2/3. And 4, 2. Okay. So we had those 4 corner points. Yes? The corners of our feasible region. The objective function in this is given here. And the question says now to find the maximum and minimum values of the objective function f equals 5x plus 8y, subject to the constraints given by that system of inequalities. So we want to find the maximum or minimum of our objective function, and it has to be one of those 4 points we just found. Okay, so we are going to plug them in. Our function says take 5 times our x coordinate and add 8 times our y coordinate. Well, what's 5 times 0 plus 8 times 0? Okay. Plugging the second point in, we have 5 times 5 plus 8 times 0, which gives us 25. Okay. We have 5 times 0 and 8 times 4 2/3. I'm going to put it back as 14/3. Go ahead, take 8 times 14. What do we get? 8 times 14. 112. So we get 112 thirds. What would that be as a decimal? Okay. So we'll go in a mixed number. 37 1/3. And then the last one, we're substituting in a 4 and a 2. So 5 times 4 plus 8 times 2 gives us what? Okay. So from those four values we just got, 0, 25, 37 1/3, and 36. What is the minimum, the smallest one? 0. Okay, this is our minimum. What one's the biggest, our maximum? All right, so what we are going to write as our final answer, we would say we have a minimum of 0. Okay, this is our minimum at the point 0, 0. We have a maximum of 37 1/3 at the point 0, 4 2/3. Okay. Now, when we shift this tomorrow to actually giving you an indication of what the x and y's stand for, we're going to adjust how we write that answer a little bit. But for now, that's all we can say. Okay. We're going to skip that. And we are done with notes for today. We're going to do those last two problems on Monday. Okay. For your homework, the first day's assignment is going to go really quickly. So what we've covered in the notes actually takes us to here. Okay. So I'm going to collect this all as one big assignment. So my suggestion is to do day 1 and get started at least on the first couple things here. You don't necessarily have to do all of that up to the 37, but if you can get a jump start on it, it's going to make your Monday much easier. Okay? I do have a couple things to go over with you really fast. We have graphed lines and parabolas. There's a couple other shapes in your homework. Anybody remember the equation for a circle? What do we have? X minus h squared plus y minus k squared equals r squared. Good. What does the hk stand for? Sometimes it's the origin. It's the center of your circle. So hk equals your center. All right. So if you don't have any numbers, if it's just a plain x squared plus y squared, then it's centered at the origin. What does the r stand for? Radius. So for example, if I said x squared plus y squared equals 16, you would say that is a circle that has a center at, centered where? Is there an h and a k in that one? So it's centered at 0, 0, the origin, with a radius of 4. So you would draw a picture, center it here, go out 4 points in either direction, right? And draw your circle. Make it prettier than that one. Yes? Remember that? So if there is an HK, you just are shifting your center point, but you're still going to move in the 4 directions, whatever that radius is. Yes? Okay. If I said y equals 5 to the x, what does that look like? What's the shape of that graph? This is exponential growth. Yes? 5 to the 0 is 1. 5 to the first is 5. Exponential growth curve. Remember those? Okay, so you'll have a couple other shapes that you have to deal with in your notes or in your homework assignment. All right. Questions about that?